Okay, thanks for having me. It's great to be back here. Especially it's great to visit in February with all this beautiful weather. Although, actually, if you come visit us, our weather indoors is much more temperate than here, so we can offer that. Yeah, so I wanted to talk to you about a proposed lower bound on the null energy. And this is based on a few different papers over the past few years. So let me just mention the kind of overlapping collaborators. So Jackson Fliss, who's a postdoc in Amsterdam, Eleni Kontu, who's a postdoc in Amsterdam, and Dimitrios, I'm not quite sure how this name is pronounced, to be honest with you, who was a master's student in Amsterdam. And we've written a few papers about this. So I guess this is a little bit the standard introduction. But so one motivating question, you could have different motivations to ask about how negative the null energy can be. But one motivating question, which I guess is the classic one, is basically what space-time geometries are allowed. And of course, general relativity doesn't really answer this question for you, right? Because in GR, any metric is OK, as long as you have the right stress tensor. So crazy things like bounces, traversable wormholes, time machines are all allowed geometries. And so in order to constrain the spacetimes, we need constraints on the stress tensor. And so we need some energy conditions. OK. So, I mean, I guess most people know this. So classically, we actually know a lot. So classically, all sensible classical theories obey the null energy condition. That's what I'm going to be focusing on here. So let me introduce this notation T++, which means contracting the stress tensor with some null vector. And classically, T++ is positive. And then already Penrose told us that assuming the null energy condition, OK, plus some other assumptions, then trapped surfaces lead to singularities. And so in particular, this is enough to rule out traversable wormholes. And bouncing cosmologies. And actually, yeah, people usually think of this as a settled story, but actually Raphael and collaborators have had some beautiful generalizations of these classic theorems in recent years. But I don't really want to go in that direction right now.
Maybe it's fair to say it doesn't rule out bounces and closed universes, which are the ones now.
But you can.
Yeah.
All right. So some combination of Raphael and his collaborators and this Penrose theorem. So classically, we know a lot about what's allowed. But the thing is that in the real world is not classical. It's quantum mechanical. and it's described by quantum fields. And every quantum field theory that I'm aware of has states that violate the null energy condition, in the sense that the expectation value of the null energy at some point is negative. And so this classical assumption is not correct. So that's kind of the question that I want to ask. So I want to ask, what energy condition is obeyed in quantum field theory? You might think that is sort of like an academic point, because GR is mostly about long length scales. But it's not, in the sense that traversable wormholes have actually been constructed within semi-classical gravity. Right, so by coupling gravity to quantum fields, people were able to construct traversable wormholes. So it's clear that actually the allowed spacetimes are qualitatively different when we have quantum fields. Okay, so what I want to mostly focus on here is a quantum field theory question, which is what sort of bounds do we have on the null energy in quantum fields. So let me mention two energy conditions that have been proven. So one is the achronal null energy condition, which says that if you integrate along a complete null ray, so let's write it like this, then this quantity has to be positive. And another nice condition, which again Raphael was instrumental in proving, is that if we zoom in, if we actually just look at the null energy at a point, that's actually bounded by some second derivative of the entanglement entropy at that point, divided by some infinitesimal area. So we have those two nice results. But even just from the quantum field theory point of view, aside from this gravitational motivation, it kind of seems like there should be some result in between that. Okay, and that's what I want to propose. So maybe I should write this over here. So the thing that I want to propose is something that we call, so this is a little bit awkward, to be honest, but so the double smeared null energy condition. All right, you'll see that, so in general, the idea is to average the null energy over some region. And basically what this is a type of energy space-time uncertainty principle that we proposed. And what it says is that let's average the null energy over some region. So if we take time and space, and we take if we average in two null directions with length sigma minus and sigma plus, and we compute the average, so I'm going to use this S for the smeared null energy, so I average over this region, then the cartoon version of our bound, I'll come to the more precise version, is that the average null energy over this region is given by a certain negative number. This is the number of degrees of freedom in your quantum field theory. And then you have some combination of these smearing lengths. And this is in 4D. We also have a proposal in other dimensions, but to be definite, let's focus on this proposal. So it's an uncertainty principle in the sense that if you average over a small region, then the null energy is allowed to be quite negative. If you average over a very large region, then this lower bound approaches 0. And this already goes back to things that were proven in certain theories for the ordinary energy by, for example, Ford. And then there's also some similar results by Fuster. So, and there's much other work that I'm not mentioning here. Yeah, so Ford had these results that involved kind of the more intuitive thing, which is just integrating T00 and just over some amount of time. And then he had a bound that was like the number of degrees of freedom over so he had some kind of bound like that.
You can't get from that by taking some limit, but it's for limit becomes null. You can get from that to your bound.
This bound doesn't imply this bound because here, like, you have some very short time-like segments where this thing diverges. So we did try to just derive this bound from that bound, and we didn't succeed at doing that. You can take a limit of our thing to derive this, to derive that bound.
I mean, most of that diverge is a limit where you take the tangent vector to the world like you know. So you could divide out by that common divergence factor, right?
I'm saying there are some small time-like segments in this parallelogram, so you can think of this parallelogram as just you could kind of tile it with time-like things, and then you can bound each one of those using the Ford bound. Yeah, that's kind of more relevant. But I think inevitably there's going to be some short time-like lines if you want to cover this whole region. Maybe there's okay. We could maybe discuss. Maybe we haven't discussed every way that. In any case, we know one way to prove this. Yeah, it might be the case that it's related to this thing. I should maybe mention. There's a couple reasons that we want to focus on the null energy. So one is that, so like bounds like this are true in certain theories, but on the other hand, we think it's perfectly fine to have a negative vacuum energy. And so in those theories, you just have or something that's close to a vacuum energy. So we don't expect a bound like this to be true in general, because when you have a negative vacuum energy, then T00 is just negative. And then even once you average over a long region, T00 is still just as negative as it was before. So that's why also, like in the classical case, people focus on the null energy condition because that seemed to be obeyed by all sensible classical theories, unlike any of these other energy conditions. And then, of course, that was also a nice input for these theorems, which involved following null vectors.
You get to choose sigma plus and sigma minus independently.
Yeah.
And this number of degrees of freedom, I mean, should I think of the right-hand side as being defined precisely by factors of order 1 things somehow, or is there some order 1 squiggliness?
Yeah, so, okay, so let me tell you what's going to happen here. So here's what we can do. So we're, which is also kind of the outline. So we're going to prove, I mean, at the moment, this is not even that well defined because what sigma is sort of depends on my precise function. So I'll prove a precise version of this bound. So that sounds pretty good. But I'm going to prove that in a free scalar quantum field theory. So that's the, and within that simple theory, then I can tell you all the order 1 numbers. Now, an important question for the future is to see if this bound is true in interacting theories. And then if so, I mean, there should be a bound that involves all order 1 factors, but then you even need to say what you mean by the number of degrees of freedom, presumably some anomaly coefficient, and so on. So there's many things that are left to do. But the proof is not very difficult. So I think it's kind of fun how it works. So I'll show you like a few of the steps there in what we did. And it'll also give you some intuition for what types of quantities are bounded and what are not. And then after that, we're just going to have I just want to mention some discussion about, because there's kind of many future steps that are important if this is going to have implications for the questions that I use to motivate it. But it's maybe worth mentioning that even aside from this motivation, I mean, this is a pretty fundamental operator in quantum field theory, the stress tensor, and understanding, the properties of that operator seems like a nice thing to do. And I think there should be simple bounds. Maybe we don't have quite the right one yet, but I think simple bounds like that exist, and they're worth understanding, even if you don't care about gravity. But are there questions? This is maybe a good time to ask. This is like the basic proposal.
The left-hand side of the inequality, that's the integral over the rectangular region?
Yes.
You said that, just a simple question, like if you said sigma plus sigma minus is 0, it converges the point, right? So, but then the bound seems to be very strong.
If you take the limit that sigma plus sigma minus goes to 0, then like the 2 volume in this region is going to 0.
Yeah, so
and then
converges to a point, the value of the t plus plus at that point, right? So.
in that limit, it becomes like the integral along a light ray.
No, I just shrink the both simultaneously.
Okay, but then this thing diverges.
Because minus is not become very weak.
Oh, sorry, there's a minus sign. Oh, sorry.
Yeah. So that's kind of the uncertainty principle aspect. If you make this thing small, then this thing can be as negative as it wants. Yeah. Okay. Other questions or comments? So, before we get to the details, there's similar bounds in every dimension that we have in our paper. Basically, you need to have the right total dimensionality here. And then because this is t plus plus, you need to have like 2 more pluses than minuses. Okay? So really what we need to prove is like that there's not a coefficient here which is infinity. Okay? But this is actually a very simple bound, and okay, we wrote the general the form in general dimensions. The dimension that's qualitatively different. So in 2D, at least for CFTs and probably in general, then this is already known. And in fact, there's no need to smear over the second direction. Okay, so t plus plus. So you just can smear over a single null ray. Okay, there's a beautiful formula that involves like the Schwartzian in CFTs. But let's just stick to this cartoon way of writing it. So you just have a bound that looks like this. Okay, and this has been proven and so on. If you go to t greater than 2, then you do need to smear over these 2 null directions. So you need to smear over a time-like direction in order to get a bound. It's kind of like, if you think about any other operator in quantum field theory, you usually need to smear in order to make it well-defined. For some operators, you can get away with just smearing in space. But for generic operators, you need to smear in time in order to make it a well-defined thing. And that's what's going on here. OK. Good. All right. So yeah, let's be a little more precise for a little while, and then we'll come to the discussion about what we can do in the future. So, and I'm going to keep on being in 4 dimensions, but it's not difficult to be in other numbers of dimensions. So we're going to use x plus and x minus for these 2 directions that we're smearing in, and then we're going to have y for the perpendicular directions. And now now I'm going to finally define the thing that I'm trying to calculate. So what we have here is we integrate over these 2 directions. We have some smearing function, and it's going to be positive, so it's going to be kind of convenient to call it g squared. And then I have t plus plus in some state psi. Whatever state is going to make the energy as negative as possible. And then, of course, we need to compare that to t plus plus in the vacuum. Okay, so that's the quantity that we're trying to bound. So just a renormalized energy momentum tensor. Okay, so now already we're gonna use this free scalar assumption. Okay, so I've been thinking about how to do this in more general theories, but you need a different starting point. Yeah.
You were saying how you need to smear the operator to make it well-defined in the first place. Do you want the g squared inside the expectation values, or?
Well, that would probably be more well-defined. On the other hand, if you're in a sensible state, the difference of the stress tensor between 2 different states, this quantity should be finite. So that's why I don't worry too much about that.
Well, I think strictly to get off the ground, you have to define that quantity smeared and then take some limit and stay finite at that level. But,
Yeah, I mean, the way I've written it, like, I think, yeah, okay, fair enough. Maybe it would have been better to just put this inside. I think this particular difference is a well-defined thing. And perhaps you're right that to make it well-defined, I should first smear this, and then take some limit that the smearing goes away. But yeah, there shouldn't be divergences in the difference between 2 states, as long as this is a...
Since you're already smearing anyway, then you might as well you could have used the g squared that you have there in the first place.
Fair enough, yes. Okay, so now I'm going to use the free...
Just make sure.
Yeah.
Space-time is a background, right? Just do it here on the background.
Yeah, so I forgot to include all of the... Okay. All right. So, yes, we're doing a very simple situation. Yeah. So there's many fun things for other people to do afterwards. Okay. So, good. So now this is a free scalar. So, yeah, am I going to write it in a different way? I think I'm going to keep writing in this sloppy way. So this t plus plus is just d plus phi. Okay, minus this same thing in the vacuum. That's fine. And now we want to write it. I'm not going to torture with you with too many equations, but this part is kind of fun. So we're gonna basically, I mean, these coincident point things are kind of annoying. So we're going to kind of separate them. At the moment, this just looks like a stupid rewriting. So we introduce this k integral. The k integral, if you do it, will give you a delta function that sets x equal to y. And you'll recover the thing above. But now you have something that involves healthier looking objects, which are correlation functions at separated points. Okay, so that seems like a pretty pointless thing to do. And actually, this technique is going to work not just for the stress tensor, but let's actually label this operator just O of x. Okay, so for any operator you might be interested in, maybe you're interested in like phi squared, then you can use this same technique. Okay, so now the key point is going to be the commutator of these two guys is a C number, because we're in free field theory. Okay, so O of x with O of y is a C number, meaning it's state independent. Okay, so this correlation function, it has an even part, it has an odd part. The odd part is proportional to the commutator, but if you look at this difference, that odd part cancels. Okay, so it means that this difference here is even under x goes to y. Okay? So we have some even function under x goes to y. And that means that this whole integral here, I think I better. So this whole integral that we have so the integrand is invariant under doing the combined thing of x goes to y and k goes to minus k. Okay, because this term is invariant, and then this invariant, this is also invariant. And just like, if you have an even function, you can only integrate it over positive x if you feel like it and add a factor of 2. So we can just integrate over like 1. We can reduce the regime of integration. So far we just have equalities. So this guy, we're going to choose to integrate over some region of k. And this is actually important because if we wouldn't do this, we would end up having some divergence. Okay, so you know what goes here. Okay, so that's the first trick. There's only one more trick, really. So this still is kind of hard because we need to constrain this correlation function in arbitrary states. So the trick that we use here is we're going to argue that this first term is positive. So this integral over here is going to be greater than 0. The way we do this is we define some pk, some operator pk, which is this integral of O of x. Oh, I'm sorry. I think I left out my my exponential here. So okay, so I define pk to be this thing, and then this orange thing is equal to the integral dk over this regime of over this range of integration that we want. Pk dagger pk. You see, because you have this k integral, and then like this x combines with this e to the ikx, g of x, and o of x to make 1p, and then all the y's combined to make the other p. Okay, sorry?
Where did the expectation value go?
So that's the whole thing now?
Yeah, so we could put it here or we could put it outside the whole thing. So this is just the orange part. Okay? All right, and then just in quantum mechanics, if you have the expectation value of p dagger p, then that's positive. Okay, so every one of these things is positive, and so the integral is positive.
That's where Raphael's smearing came in, right? In that form, you might have as well just have g of x inside the integral.
Yeah, this is somehow like a much happier thing than the things I was writing above. Yeah, so there's probably a more rigorous way of never writing these ugly things that I wrote. Okay, I want to mention that there's, so it's not something I'm trying to improve at the moment because I'm trying to go beyond free field theories. But there's kind of an inefficiency here, which is that this thing is not just positive, but generically, like all these pKs don't commute with each other. So there's actually no state where this thing is equal to 0. There's actually no state that's annihilated by all of these pKs. That would be possible if they all commuted, because then you just find the state that's annihilated by all of them. But since they don't commute, that's not possible. And so when I say this is positive, that's not the strongest thing I could say. It's actually larger than some positive number. I have some formulas for that, but they're not very beautiful. So I'm just gonna say this.
Is the convergence of the integral of the last line of it is guaranteed?
Sorry?
Convergence of the integral guaranteed?
This integral?
No, yeah, the one above, yeah.
This one.
Yeah.
That's what we have to see. So that's the main moment of the question of suspense, is whether this bound will converge.
Because if you have to regulate at 0, then of course regularization may break.
Yeah. I think the thing is that this difference kind of has to be finite in any sensible state, because, okay, sensible states have to differ by a finite amount from the vacuum. But then once I break it up, we could be in, maybe I threw away infinity here. If I would do this, like if I would choose this domain in a dumb way, I could throw away infinity, and then I'm going to get some useless bound. So that's what we have to see. Okay, and the reason we have this inefficiency, I think, is that I chose to represent this delta function by some integral over k's. So we sort of used these. We kind of used the momentum basis, but that wasn't actually like the smartest basis. It's not adapted to our smearing function. So there's probably a way of redoing this, where you use a smarter definition of a smarter representation of the delta function, and then you might get a stricter bound. Okay, but this is good enough for today. So now we have simply the bound. Yeah, sorry. So I suppose I should have written a factor of 2 here, because I limited my region of integration. Although in general, you should look at the paper if you want to know about the factors of 2. So I just throw away this positive thing. And then I have a certain negative number here, which is just this integral over k. And then this correlation function in the vacuum. Okay, so now I'm going to start skipping steps and so on. So this is the part I want to do carefully. Because you see, now we have a bound on the expectation value in the arbitrary state psi. But on the right-hand side, we have stuff we can work with. So we just have correlation functions in the vacuum. We know what those are. And now we can just like do these integrals and everything. So this is kind of like the I'll write a nicer version of this formula, but this is kind of like the main thing that you that we accomplished with this thing. So are there questions about what happened? Because now we just kind of go to the consequences.
Arbitrary dimensions, right? You wrote the y squared up there at the top, so it's not, we're not in it.
Yeah, this thing, and even I wrote these D2x, but that actually didn't even matter. So you could just make this P, make the total space dimension Q, and then yeah. So there's a general result where, okay, maybe this is not. So yeah, the general thing you can prove is that you're trying to compute expectation value of this O squared smeared, and then it's bounded by this thing.
Sorry, but are you integrating over all space-time dimensions or just over the two null dimensions?
Yeah, so I'm just integrating over these two null directions. But actually, you could generalize this and you could change these 2's to p's. So you could integrate over whatever, if you prefer integrating over like a light cone or something, you could do that. But for the moment, to be definite, I'm just integrating over these two directions.
Even if you're d greater than 2?
Yeah.
Okay.
Yeah, because it's kind of like the smallest integral that we can do that's going to lead you to some operator that's bounded below. But then, yeah, you can definitely ask, like, yeah, but maybe it's nicer to integrate over like a causal diamond. There's other things that you might want to do, and all of this stuff goes through in the same way.
Maybe some comment my question and about the K integral.
Yeah.
It's not enough to say that the function is an even function. That may be enough to say at least you can.
Sorry?
Because delta function must be even function.
Yeah.
So that's already saying that whatever you do in K integral, like regularization or anything, it's just a symmetric with respect to change the equal to 0.
Yeah.
That's probably not enough.
Okay, I think I agree with you. Yeah.
So I'm commenting on
Okay.
question.
All right. So fine. So now, yeah, let's jump ahead. So if you want to actually evaluate what this bound is, the most convenient thing is to go to momentum space. So let's write this correlation function in momentum space. So we have some O tilde of P, O tilde of P prime. So we just Fourier transform everything. This is going to have some delta function. I'm just Fourier transforming in the directions that I'm integrating in. Okay, so everything is in this 2D plane. Okay, so I have some delta 2 of P plus P prime. And this, just to be clear, this thing that we're talking about is the Whiteman function. Okay, so it's not like time ordered or anything like that. And as a result, on this side, it has some theta function that forces P0 to be positive. And then it also has a delta function, which forces the thing to be on shell. And then potentially some more things that I'm not going to write explicitly. So, but in general, just because of the symmetries of the problem, you have these. Yeah, sorry, let me maybe not. So this is a general thing. This is true for the massless case. So let's not maybe specialize to that quite yet. Okay, and then if you plug this in, you get some kind of integral. This looks like. Some integral in momentum space. We have the Fourier transform of the smearing function. And then we have an integral over the momenta. We have this Green's function. And then, because we had this K0 being positive, if you follow it through, then this P0 has to be smaller than L0. Okay?
Say again what L0 is?
L is the thing that's being integrated here.
What is L0?
Oh, sorry. So these momenta have two components, which I'm going to call L0 and L1. So yeah, I think I was unclear about that from the beginning. So here, when I was picking this domain of integration, I chose a particular component of k, the time component of k. So I chose the frequency to be positive. That's, by the way, another place where you can try to get a stronger bound, is you can pick a different domain that you want to integrate over.
So the delta function that appears in that equation, the delta squared, that refers to the two vector plus T0 and T1.
Yeah. Yeah, so I use these like p's for two vectors, and then I use the 0 for just the 0 component of them. Okay. Yeah, and then you can kind of see what's going on here. That's why I mentioned this theta function. So this frequency here needs to be positive, but then it can't be too positive because of this condition, which it inherited from here. And so otherwise this integral would diverge at large frequencies. Okay, so once you do this integral, you just get some function of L0. And then as long as your smearing function decays at large momenta, then everything will be happy. Let's write it more explicitly for the massless scalar. And now we are going to be in 4D. And so what this looks like is just let me maybe not worry about the 2 pi's and so on. But we just have this integral over momenta. We have the Fourier transform of the smearing function. And then we have this L0 to the 4th. So I don't know. If you want, you can write it back in position space. So what do you think? Is that a good bound? These are time derivatives. There may be some aspect of this bound that you might dislike. No? You're satisfied? Yeah?
Do you have any restrictions for D, or is that general?
For?
For D, the smearing.
I don't have restrictions. This is valid for any G. But of course, if you pick a bad G, then this thing will diverge. So in particular, actually, if you pick like a G that's sort of inspired by the modular Hamiltonian, then like these derivatives diverge at the endpoints, and then you get infinity. So basically like your smearing function, maybe you feel like smearing over a finite region. But then you need to go to 0 smoothly enough so that this expectation value of moment is finite. So this is a valid formula, but for any G, but sometimes it will give you infinity.
Just a question on derivations. Was it important to first fix K0 to be positive before we set the positivity argument of the pKs, or are the pKs already positive for even if K is not taken with K0 positive?
No, they were already positive, but they're kind of too positive. So what's kind of going on is that the potential divergences are in this other half plane at negative k0. And so I needed to first restrict this before separating these two terms. Okay, so we could have not done this whole thing of restricting to some k0. Then we'd just be integrating over all k0 here. And it's not obvious at this point. Well, maybe if you know exactly what this thing looks like, you can see at this point that we're going to have a problem. But you can see at this point, then you just wouldn't have this restriction. And then this integral would just diverge. And you know there's potential divergences here, right? Like because this 2-point function at coincident points diverges. So that's the thing that you need to be careful or lucky with.
Right, so the vacuum expectation value would have diverged very negatively, so you
Yeah.
that needed to be compensated by the positive.
Yeah, exactly. Yeah. It's kind of like at all k's, this difference is well behaved. But then for some k's, they're each well behaved separately. And so, yeah, that's...
The claim is that if you choose your D to sort of have order over characteristic sigma plus and sigma minus, and then it
Oh, yeah, we have to get to the cartoon. But yeah, I still have a question, though. I thought somebody was going to complain about this formula for some reason. And I didn't hear any major complaints yet.
So why, isn't sigma plus, they're on top?
OK, you want to know how it becomes this formula?
Right. Yeah.
OK, yeah, we can talk about that. But really, nobody dislikes this formula? There is something bad about this formula.
We're a naive bunch, man.
No, this is like one of your... OK, the annoying thing about this formula, let's say, look, if we look here, is that it doesn't look Lorentz invariant. Because like, why does it have this L0 sitting here? Or why does it have like this time derivative? Right? If I had like grad g or something, then you should be happy. But when I just write this time variable, then it looks a little bit ugly, right?
So that was your choice of chamber on the k minus k.
Yeah, exactly. So right. So I chose this time variable when I chose this thing. And so, yeah, so what you can do now is you could optimize over your choice of t. Which means just you can boost this thing. So you can just pick different things here. In your final thing, instead of writing L0, you can write like the boosted version of L0. Okay, and then you have sort of like a clunkily defined Lorentz invariant thing, which is that the bound is this. Extremized over, I mean, this is a true bound for any choice of frame you want to pick, but you would probably like to pick the direction that will give you the smallest number here, right? The smallest negative value. Okay, so well, because the way I wrote this bound, before I say I'm going to optimize over t, then there's a choice of time variable.
Yeah, but as long as it holds for any choice, it's fine.
Yes. Okay. But I didn't say that yet. Then we have some operator on the left. Anyway, whatever. It's fine. It's a beautiful bound. Okay, so that's the bound. Yeah, it's maybe worth mentioning briefly for the massive scalar. Then this bound is kind of qualitatively different. So we have this same kind of stuff appearing here. But then we have a L0, then we have L0 squared minus m squared to 3/2. And then we have some theta function saying that this quantity has to be positive. Basic frequency needs to be larger than the mass. So why is this qualitatively different? The point is that if the mass is large, then it basically forces it to be at large frequencies. And then let's say your smearing function is a Gaussian. Then that forces you out into the large frequency tail of your smearing function. And so, for example, if G tilde is Gaussian, then you get some e to the minus m squared, sigma squared type of formula. Okay? So it's kind of like the fields that are massless at the length scale that we're talking about are the ones that can contribute the negative energy. And if they're massive, then you might as well just forget about them. Okay. So yeah, let's maybe recover the cartoon version and talk about the future directions. Okay. So to get this cartoon, what we want to do is let's go to the frame. Whoops. So we have a much longer argument in our paper, but the quick and dirty argument is we can change sigma plus and sigma minus by doing boosts. So we can just go to the frame where these two things are equal. Okay. To get this cartoon version, we also have to assume that these G tildes are boring, right? Because a general smearing function, it just has more than one length scale in it, so there's not a single thing that you call sigma plus. So we're going to assume that this thing is boring. And then maybe we're going to assume, to kind of agree with this picture, we're going to assume that this smearing function is a product. Okay, so we have some, that's a little bit what this cartoon means. You have some smearing function in the plus direction and some smearing function in the minus direction. Okay, so then if we look at this bound up here, it's nice to kind of think of this G squared as being like a probability distribution, like a probability density. And here we're computing like the expectation value of the frequency to the fourth. Right? It's just an ordinary classical probability distribution. That's kind of natural because it's natural to normalize the smearing function so that it integrates to 1. Okay, so what we have here basically is a formula that says that the smeared stress tensor is this kind of expectation value of L0 to the fourth. And then we would just write this as L plus L minus to the fourth. You can show because of the symmetries of G squared that only the even moments are non-zero. So you have L plus to the fourth. You have, L plus squared, L minus squared. And you have L minus to the fourth. Actually, that's not really how binomials work, is it? Some number here. Yeah, 6. Okay. Good. Good. And now, since this is like a boring function, like a Gaussian, so this L plus to the fourth just becomes 1 over. This is the width in momentum space, so it's 1 over the width in position space. And now we're only doing cartoons, so we don't need to keep this 6. Okay, but then we were in the frame where sigma plus and sigma minus were the same. Okay, so the cartoon version in this frame is just minus 1 over sigma to the fourth. Okay, and then you can go through the trouble of transforming to a different frame. But of course, you have to get the thing which transforms in the same way as the thing on the left-hand side. And you get this cartoon version. Okay, so you basically just need to see how this thing transforms under boost. And we do that in a very explicit way. Okay, so yeah, questions?
Can you write down the master case for the cartoon?
For the cartoon. Yeah, the massive case is a little bit annoying to write down because this is sort of the best thing I can write down because it's like it pushes you into if the mass is large, it pushes you into the tail of the probability distribution or the smearing function. But then the dependence on the mass, it depends on the details of your smearing function. So like is it Gaussian at large frequency or not? So it kind of depends on those details.
For cartoon, it's 0.
Yeah, thank you, thank you. Yes, you're right. You're right. Okay. Yes. So it's this thing for the mass squared less than sigma plus sigma minus, and it's 0 for the mass squared much bigger than sigma plus sigma minus. Thank you. Okay. Good.
Well, that's the meaning of n degrees of freedom. The number of
Yes.
numbers.
Yes. Yes. Yeah. So I mean, yeah. And then you can put an n here if you have many light things, right? So what n means is like the number of relativistic degrees of freedom at the scale sigma plus sigma minus. Okay, within this free field theory analysis. Yeah. Yeah. So this is the bottom line. A simple result. It's the number of relativistic degrees of freedom divided by things that are given by dimensional analysis. But it's a nice result. It's a nice simple bound on the stress tensor. Okay, so let's talk about the many things that would be nice to do. So the most obvious thing is like general quantum field theories, or maybe just to start with, maybe CFTs, interacting CFTs. There's ways that people prove like the average null energy condition. And you might think that those same techniques should kind of work. One thing is that if you take a causal diamond and then you boost it, you get the ANEC operator. So you might think that this thing, or a slight variation on this, can be related to the ANEC operator by a conformal transformation. I don't know. These are vague. These are vague statements. So we're trying to look into that, but.
But it seems that, you were saying, when you were saying at the beginning that this sort of falls in between the QNAC and the ANAC, that would be the sense. So I was wondering whether you actually meant that the big sense in which it falls logically between them. Like, there's a sense in which you can prove the ANAC from the QNAC, but only in the restricted set of spacetimes to which the QNAC applies in the first place.
Yeah.
But then the implication holds. Is there some story like that here where you can interpose the DSNAC and have it be?
Well, it's true that this thing implies the ANEC. So in that sense, yes.
That you just wrote down.
Well, I don't know what I was writing here. I think I was writing here that you can think of the ANAC as you took some diamond and then you boosted it. But it's a correct statement is that this result implies the ANEC. I haven't connected I haven't seen how to connect in an interesting way to the QNEC because you have this, then you have this S double prime, and I don't know exactly what to do with that. The second obvious thing is like curved space-time. And an interesting question there is whether you get some extra terms, right? Because now you have another scale, which is the curvature scale. And for example, there's some results by Choi and collaborators, I believe, that says that like the achronal ANEC can be violated in curved space. That's at the level of quantum field theory in a curved background, okay? So there's a different question if you have like a self-consistent solution where your quantum field theory is supporting the geometry. And there, to my knowledge, this achronal ANAC is always preserved, as far as we know, and we kind of believe in it. But an obvious question is just what's true about quantum field theory in curved spacetime. And then there need to be some corrections. Then a different direction, obviously, is if you just assume this condition, then you would like to prove some singularity theorems. We did that with a slightly different energy condition, but roughly, in the Penrose theorem, if you had some trapped surface, then that led to singularities. And roughly what's going to happen here is that you need the expansion to be less than some number to account for the fact that there might be some amount of positive energy. And you need to be less than that number over some little region. Sorry?
You need to account for the fact that there might be some negative energy.
I'm sorry, yes. There might be some neck violation. And so you need to strengthen your starting assumption. So we showed how to do this in one particular case, but I think there's it's kind of nice to think about these things together, because at the level of quantum field theory, there's a lot of different kind of operators you could consider. But if you think about what's going to be useful for singularity theorems, that probably helps to narrow in on, to zoom in on interesting operators. I should mention here that, like, there's this interesting approach through the quantum focusing conjecture and so on. There, I think the statement was that if we look at the quantum expansion and that's negative, then that would lead to singularities. But I guess there's interesting asterisks in this conclusion. So that's maybe something that's fun to discuss in the.
There's a theorem by Aaron Wall, right, that shows this.
Okay, I think it depends on the assumptions. I think we were discussing a case yesterday where we had a negative quantum expansion and we didn't have a singularity. Right. So we had a quantum trap surface without a singularity. So
This is the Wall's theorem is more like Penrose's, that it assumes that there's an all-compact size.
right. Okay. So
Examples like that. So I think the examples we got also have singularities, just like this.
okay. Yeah. All right. So anyway, yeah. Okay. Anyway, there's many interesting questions. The kind of bottom line is I feel like this is kind of a simple, interesting operator that seems to be bounded in a simple, interesting way. And I think it's kind of interesting to understand in quantum field theory. And I think that will be useful in understanding what kind of spacetimes we can have in semi-classical gravity. All right, thank you.